students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss problems on question bank. Regarding question bank. So here we are going to discuss first module. The first module, which is amplitude modulation. So today we are going to solve question bank problems in amplitude modulation. Okay. So what is module 1? It is regarding to the amplitude modulation. So what are the course outcome? First says outline the basic concepts of communication system, need of modulation and fundamental elements to realize amplitude modulation systems. So this module totally regarding to the amplitude modulation systems. Okay. So today problems are all on amplitude modulation like DSP, SSP. So all types of amplitude modulations are covered in this session. Okay. So starting the question bank. So the question bank, which consists of 3 parts. So part A is the problem solving and critical thinking questions. Here we give the problems. Okay. So it is critical thinking problems are given. Whereas coming to the part B, long answers of that. Coming to part C, short answers. So this question bank consists of 3 parts for every module. Okay. So this is analog digital communications. So in analog digital communications, we're having 5 modules. So all the 5 modules consist of 3 parts. Okay. So let us start the problem session. Yeah. So the first one is consider an AM signal m of t is equal to 1 plus a cos omega mt into cos omega ct, where the message signal frequency omega m is equal to 5 kHz and the carrier frequency omega c is equal to 100 kHz. The constant a is equal to 15. Can this signal can be demodulated by an envelope detector? So here, what are the parameters required for demodulated signal using an envelope detector? So this is the concept of this problem. Okay. In this problem, they given m of t. M of t is equal to 1 plus a cos omega mt into cos omega ct. Okay. So they given an AM signal. So regarding the AM signal, we are going to find this signal frequency and carrier frequency, but they directly given. So first you go to substitute what the values are given in that signal. Okay. So generally carrier signal is represented as modulated signal is represented as S of t, and M of t is the message signal and C of t is the carrier signal. But in some textbook notations, they may use different notations. But generally, any modulated signal can be used. S of t can be represented as S of t. Okay. Now my S of t is equal to 1 plus A. What is A? Here the constant is that the value is 15 and cos omega mt. So cos 5 t, cos 5 t, whole brackets of cos omega ct. So cos 100 t, this one. So for this signal, the envelope detector can demodulate or not. Thus, okay. So here we given some answer. Yes, The envelope detector is a simple and commonly used demonic technique. First, what is envelope detector? That you must know. Okay. So the envelope detector is a simple and commonly used demonic technique for extracting the message signal from an amplitude modulated signal. So in order to successfully demodulate the signal using this technique, certain conditions must be met. What are the conditions? Here, minimum value of the carrier signal amplitude should be at least 2. Should be at least 2. So coming to this one. So here we're having 15. So 2 is required. So we have sufficient amount of amplitude is there. So this signal can be demodulated by an envelope detector. So this is the answer. So for this answer, first we go to write the standard equation and substituting the given values. Then after you are going to what is the condition for the envelope detector that you are going to know. Okay. Yeah. Coming to the second problem. Find the percentage power saving when the carrier and one of the sidebands are suppressed in an AM wave modulated to a depth of 100%. Second one is a 50%. So depth of modulation is nothing but modulation index. So in this problem, they given two modulation indexes, two cases. Okay. So let us start this problem. So total power in AM. What is AM? Amplitude modulated signal. So what is the formula? Total power is equal to carrier power into 1 plus m square by 2. So literally here P of t is equal to Pc into 1 plus m square by 2. Pt is the total power. Pc is the carrier power. What is m? Modulation index. Here what is given? First case 100%. So 100% means the mu value is or m is 1. And one thing here, the modulation index can be represented as mu or m, what it may be. Yeah. After substituting m value, what you got? Pt is equal to 1.5 Pc. So why? Because 1 plus m square, m value is 1, 1 square 1 by 2 gives 0.5. So 1.5 Pc. Pt is equal to 1.5 Pc. Now power in one sideband is given in Ps equal to Ps into m square by 4. So what is Ps? Sideband power or power in one sideband. That is equal to carrier power into m square by 4. So you know the m value. M value is 1. So 1 by 4, 0.125. Sorry, 0.25. 0.25 Pc. Okay, this is sideband. Now the power saving is equal to total power minus sideband power divided by total power. Okay, so you know the total power. The total power is 1.5 Pc minus sideband power 0.25 Pc divided by total power 1.5 Pc. So here the Pc is common, you can take outside. So here this value is 1.25 Pc divided by 1.5 Pc. So this Pc is going to cancel. So we got 83.3% for the first case. For the first case, m value is equal to 100%. And second one, they given m value as 50%. So 50% is 0.5. M value is 0.5. So my total power is equal to Pc into 1 plus m square by 2. Same formula. So here also you go to substitute. What is m value? 0.5. So 0.5 whole square. So 0.25. Again 0.25 divided by 2. So finally you got 1.125 PC. 1.125 PC. What is this one? Total power. And again sideband power. That is equal to PS equal to PC into M square by 4. So finally my PS value, sideband power is 0.0625 PC. Why? Because here they ask how much power is going to save when the modulation index or depth of modulation is changing. For 100% you got 83.3%. Okay. Now here my modulation index is reduced to 0.5. Now the power saving formula is total power minus sideband power divided by total power. So it is equal to 1.125 PC minus 0.0625 PC divided by 1.125 PC. So here we must need the calcium. So without calculator you can't solve these problems. So now my power saving is 94.4%. So you already observed for M value is 1, you got 84. Where M equals 0.5, 94% is having. Okay. So this is the second problem. Okay. So coming to the third problem. So what the third problem says, the output voltage of a transmitted signal is given by V is equal to 500 of 1 plus 0.4 sine 3140 t into sine of 6.28 into 10 power 7 t. This voltage is fed to a load of 600 resistance. Determine the message carrier power, total power. Okay. So here they may use any notation, that is S of t, V of t, whatever it may be, the given signal. Okay. So this signal is fed to a 600 resistance, load resistance. So what is the message and what is the carrier frequencies and carrier power, and finally total power. Okay. So here we are going to comparing the standard equation. By comparing the standard equation, you are getting these values. You go to find. Okay. So what is the standard equation? AC into 1 plus mu sine 2 pi FMT into sine 2 pi FCT. So here the given V or V of t, whatever. So this is my standard equation. So here I am going to comparing for the above equation. So here you can see AC is given as a 500 volts. So AC is 500. So AC is 500. And again sine 2 pi FMT. So this is sine 2 pi FM, which is equal to 3140. So by using calci, you can find FM value. So FM value is 50 Hz. And again comparing the carrier frequency, 2 pi FC is equal to 10 power 7, 6.28 into 10 power 7. And finally FC is 10 megahertz. Okay. So here just I am going to comparing the given equation with the standard equation. Then I am getting message frequency and carrier frequency. And at the same time AC carrier voltage. Okay. Now we are having a mu also. Why? Because go for this previous one. Here this is the mu, and another one is mu is also 0.4 modulation index or depth of modulation. Okay. So now by using those mu value and carrier voltage, I am going to find the carrier power. That is nothing but PC. Carrier power is nothing but PC. So this is my PC. So PC is equal to AC square by 2RL. So what is AC? This is 500. So 500 square. So 500 to 500 divided by 2RL. So what is RL? Low resistance. So in the problem they given low resistance. So once again go to back. So here the low resistance is 600. Okay. So RL is 600. So what are we doing? PC is equal to 500 into 500 divided by 2 into 600. So by using calculus you can easily solve this one. Okay. So after solving that, 208.33 watts. So here power is must be in watts. And finally the total power. So the formula is PT is equal to, so PT is equal to PC into 1 plus mu square by 2. So we know the PC 208.33 into 1 plus mu square. Mu value is 0.4 square by 2. Then we got 224.99 watts. 224.99 watts, approximately 225 watts. Okay. So this is the third problem. Now coming to the fourth problem. So in fourth problem, a certain transmitter radiates 6 kilowatt with a carrier unmodulated and 9 kilowatt when the carrier is sinusoidally modulated. Calculate modulation index if another sine wave is simultaneously transmitted with modulation index of 0.5. Determine the total radiated power. Okay. So here they given carrier power and total power. Okay. So we are using the same formula. For that one, total power is equal to carrier power into 1 plus mu square by 2. But the given carrier power is 6 kilowatt and PT is 9 kilowatt. Okay. So we are going to substitute and find the answer. Okay. So the given mu is equal to 1. Okay. So mu is 1. For initially mu is 1. But another sine wave is simultaneously transmitted with mu equal to 0.5. Here, two conditions. If another sine wave is simultaneously transmitted with a modulation index of 0.5. Okay. So by using this, here you go to find the mu value in the first case. Why? PT. What is the PT? PT is 9. PC is 6 into 1 plus mu square by 2. Okay. So I am going to find the mu value. So 9 by 6 is equal to 1 plus mu square by 2. Okay. So mu square by 2 is equal to here 9 by 6 minus 1. Okay. 9 by 6 minus 1. So after solving this all, you are getting mu value is 1. Mu value is 1. So after finding this mu value, another sine wave is simultaneously transmitted with the modulation index of 0.5. So here we are getting two modulation indexes. So that's why here we are getting the total mu value. Okay. So here the value, the formula is square root of mu1 square plus mu2 square. What is mu1? 1. 1 square plus 0.5 square, and this total is within the root. So finally you got mu t is 1.11. After getting this 1.1 value, mu value, then you go to substitute. Okay, so again the total power is equal to, so this is the total power, Pt is equal to Pc into 1 plus mu square by 2. So substituting all these values, my Pc is 6 watts. So Pt is equal to Pc 6 watts plus 1.11 square by 2. So solving these values, you are getting this value 9.75 watt. Okay. Now coming to the fifth problem. An audio frequency signal m of t is equal to 10 sine of 2 pi 500 t is used to amplitude modulated a carrier of c of t 50 sine 2 pi 10 to the power 5 t. Calculate the modulation index, sideband frequencies, bandwidth required, and total power delivered to the load of 600 watts. Okay. So here we given m of t and c of t. M of t is the message signal. C of t is the carrier signal. Why? Because for modulation we must require these two signals. They are the basic signals. Without message or carrier, you can't do modulation. Okay, so they given the primary signals, and then by using that we will calculate the modulation index. Okay, so first comparing the m of t. M of t is am sine 2 pi fmt. Why? Because this is the standard one. Am sine 2 pi fmt, where c of t is equal to ac sine 2 pi fc of t. So here by comparing am, I got am is 10, and again I comparing ac, it got 50, and comparing 2 pi fm, 2 pi fm is equal to 2 pi 500 t. So this 2 pi cancels. What my fm? 500 hertz. Again my 2 pi fc t, not t, okay, no problem. It is equal to 2 pi into 10 power 5. 2 pi into 10 power 5 t. So this is going to cancel, and 2 pi is cancelled. So my fc is 10 to the power of 5 hertz. So 10 to the power of 5 hertz is equal to 100 kilohertz. Okay. So now I get to whatever the basic data I recovered from the given problem. By using the data, I am going to substitute in formulas, then I get the values. So first one is the modulation index. So modulation index is equal to mu is equal to am by ac. So here what is am? Am is 10 divided by 50. AC is 50. So 10 by 50. So 0 cancel, you get 0.2. So my mu value is modulation index is 0.2, and sideband frequencies. So for sideband frequencies, fc plus fm, that is equal to 100 kilohertz plus 500. Why? Because my carrier frequency is 100 kilo, my message frequency is 500 hertz. We are having two sidebands. For amplitude modulation, we are having two sideband. So another name for amplitude modulation is double sideband with full carrier. So I am having two sidebands. So one sideband frequency is 100.5 kilohertz, and next one, this is a upper sideband USB. It's simply called as USB, upper sideband. and another is the lower sideband. This is my lower sideband. Fc minus Fm. So that is 100 kilohertz minus 500. That is equal to 99.5 kilohertz. Okay. So when you see the spectrum, this is just like this one. This is 0 and this is a frequency. So this is my USB and this is my LSB, lower sideband. Okay. So this is the frequency spectrum. And next one is the bandwidth requirement. So how much bandwidth is required? So just 2 FM. So FM is 500 Hz. So 500 into 2 get 1 kilohertz. Okay. Now coming to the total power delivered. Why? Because RL is 600 given. So by using that 600 load resistance, you can find the carrier power. Why? For the total power formula, PT is equal to PC into 1 plus mu square by 2. We know the mu value. We know the PC. How? PC is equal to AC square by 2RL. Okay. So AC value is 50. 50 square divided by 2 into 600. By solving that one, we get 2.08 watt. After getting the PC value, we are going to substitute in the above formula. PT is equal to PC into 1 plus mu square by 2. Okay. So then you get PT is equal to 2.121 watts. Okay. So fifth one is completed. And now sixth problem is a DSB-SC signal. DSB-SC means double sideband suppressed carrier. We're coming to the AM. AM is a double sideband. AM also double sideband, but with full carrier. That is FC. Here I'm going to suppress the carrier. Why? The main disadvantage of AM is wastage of bandwidth. We are having 2 sidebands, so it takes more power and more bandwidth. So I'm going to reduce these 2 very essential parameters. One is the power and bandwidth. So we move for DSB-SC. Okay, so that is the DSB-SC. Now the DSB signal is to be generated with a carrier frequency FC is equal to 1 megahertz using a non-linear device with an input-output characteristic V0 is equal to A0 Vi plus A0 Vi cube, where A0 and A1 are constants. The output of the non-linear device can be filtered by an appropriate band pass filter. Let V0 is equal to A cos omega ct, A cos 2 pi fct plus m of t, where m of t is the message signal. Find fc dash. Here, this is fc dash. Okay, thus you go to find. So here, let vi is equal to AC dash cos 2 pi fc dash t plus m of t. Okay, so m of t is the message signal. So what they given? V0 is equal to A0 Vi plus A0 Vi cube. Okay, so here they give a Vi. So mistake, this is Vi. Okay, so we are having Vi. So we are going to substitute in this equation. V0 is equal to A0 Vi plus A0 Vi cube. Okay. Yes. So here we are going to write B naught is equal to A naught into AC dash cos 2 pi FC dash T plus M of T plus A1 AC dash cos 2 pi FC dash T plus M of T whole cube. Why? Here the given V naught is equal to A naught Vi plus A1 Vi cube. A1 Vi cube. Okay. So here I am just substituted Vi value, input voltage, in the above nonlinear equation. Okay. So V naught is equal to A naught AC dash cos 2 pi FC dash T plus A naught M of T plus, here coming to the second part, A plus B whole cube. You can see A1 into A plus B whole cube. Here A value is AC dash cos 2 pi FC dash T plus B value is M of T. So it is in the form of A plus B whole cube. So what is the formula? A cube plus 3 square B plus 3AB square plus B cube. So A1 into AC dash cos 2 pi FC dash T whole cube. Okay. Next, 3A square B. So 3A square. So this one. AC cos 2 pi FC dash T whole square B M of T plus 3A1 AC dash cos 2 pi FC dash T into M square T 3AB square plus B cube. So A1 M of T whole cube. This one. So this completed. Now this total signal is passing through a non-linear device. Here the output. So that means we are going to passing the signal through a band pass filter. So the band pass filter which is going to reject unwanted signals. Okay. Here unwanted means higher signals is coming. Okay. So V naught is equal to A naught AC dash cos 2 pi FC dash T plus A naught M of T. Okay, here you can see FC dash T whole cube. FC is 1 megahertz whole cube. Okay, so this is unwanted. And second one, 3A1 AC dash cos 2 pi FC dash T whole square. Okay. So here I'm taking this 3A1 AC dash cos 2 pi FC dash T whole square M of T. Okay. And as remaining, this is the M square T is unwanted. M cube T is also unwanted. And this one is going to unwanted. So out of these three terms, one is A naught AC dash cos 2 pi FC dash t plus A naught M of t. So A naught M of t is a message signal. So that's also not a DSB signal. Okay. So here we are taking this FC dash. 2 FC dash is equal to 1 megahertz. This one is the DSB signal. This only 3A1 AC dash cos 2 pi FC dash t whole square M of t is the DSB signal. So DSB signal having the carry is 1 megahertz. So we are going to equating this 2 FC dash is equal to 1 megahertz. So FC dash is equal to 1 by 2 is 0.5 megahertz. So this is the what we required one. Okay. Yeah. So seventh problem. The RC load for a diode envelope detector consists of a 1000 picofarad capacitor in parallel with a 10 kilo ohm resistor. Calculate the maximum modulation depth that can be handled for a sensor modulation at a frequency of 10 kHz if diagonal peak clipping is to be avoided. So here we are going to avoid the diagonal peak clipping. Okay. So first I will write what are the given. RC is 10 kilo ohm and C is 1000 picofarad. Okay. And FM is 10 kilohertz. So from this angular message signal frequency is 2 pi FM. That you can write 2 into 10 kilo. That's 2 pi 10 kilohertz. So what is the formula for diagonal clipping? Diagonal peak clipping avoided. So okay, to avoid the diagonal clipping, time constant is designed RLC less than equal to 1 by omega m square root of 1 minus m square divided by m. Okay. So here we are going to find the modulation depth. That means maximum modulation depth, modulation index. They given RL, they given C, they given FM. So from that FM we are going to find the omega m. So what are you going to find? We are going to find the m value. Okay. For that, m divided by square root of 1 minus m square is equal to 1 whole divided by 2 pi into 10 cube into RL 10 kilo ohm into 1000 picofarad. Okay. So this is my FM, this is RL, this is C. Once again go to back. So this is my formula. RL C less than or equal to, this is the condition for avoiding the diagonal peak clipping. So by using this condition, I am going to find the m value. Okay. So m, for m equal to here, m divided by square root of 1 minus m square, the cross multiplied. So that's why you go to substitute all this value. So this one. So by using calcium, you go to solve all this one. And then here 10 to the 4, 10 to the 4, and this 3, 10 cube. Okay. So finally, we're having 1 by 2 pi into 10 power minus 1 only. Why? Because pico is there. So minus 12 is going to all this 11. Here 3, 6, 7, 4, 11. So 10 power minus 11 is there. So 10 power 11 is there and minus 12. So adding, getting 10 power minus 1. So it is 10 divided by 2 pi, that is 5 by pi. Okay. So here m divided by square root of 1 minus m square is equal to 5 by pi. So square root is removing, 1 minus m square is equal to 5 by pi whole square. Okay. So m square is equal to 5 by pi whole square into 1 minus m square. So by using calci, here you are going to find out 5 by pi whole square is equal to 2.53 into 1 minus m square. And finally solving all this value, m value is 0.84. 0.84. So this is my maximum modulation depth value. Okay, here this is. So an audio frequency signal m of t 20 cos 8 pi 10 cube t is used to generate a DSBSC for carrier of C of t is 20 cos 2 pi 10 power 60. Calculate the modulation index. Here index is missing. Modulation index, efficiency, sideband frequencies, bandwidth required, and finally total power. Okay. So already we discussed m of t is equal to am cos 2 pi fmt, and c of t is equal to ac cos 2 pi fct. And one thing here, for every time c of t is greater than m of t. That's already you know. Okay, so that's why here fc is in terms of 10 power 6, where fm is in terms of 10 cube. One is kilo and one is the megas. Okay, so by comparing this, you get am is equal to 20, ac also 20, fm is 4 kilo. So why? Because 2 pi fm is equal to 8 pi 10 cube. 8 pi 10 cube. So this pi 4 times. So fm is 4 kilohertz. Okay. And similarly fct. Okay. So comparing 2 pi, fc is equal to 2 pi into 10 power 6. So this 2 pi cancel. fc is equal to 1 megahertz. Okay. After getting this, we can find the modulation index, mu equal to am by ac. So that is the mu value is 1. Okay. And these are the formulas what are required. Efficiency. For efficiency, that is equal to P USB plus P LSB by PT. So what is USB upper side band? LSB is the lower side band divided by total power. So PT is equal to AC square into AM square by 4R. And this sideband power is equal to AC square AM square by 4M. So when you substitute to the same values, so the eta is equal to 1. The efficiency is 1. And sideband frequency already know. Upper sideband, lower sideband. So this is USB and this one is the LSB. So for USB, FC plus FM. For LSB, FC minus FM. Okay. So you know the FC value, you know the FM value. So substituting all this, you get FC plus upper sideband is equal to 1.004 megahertz and LSB is the 19.06 kilohertz. Okay. So this is the way. And bandwidth required is 2 FM, 2 into 4, 8 kilohertz, and total power is AC square into AM square by 4R. Okay. So substituting all these values, you get total power is 40 kilowatt. Okay. So that's why calci is must. Without calci, we can't do. Okay. Yeah. Ninth one. An AM modulator has an output given by x of t is equal to a cos 400 pi t plus b cos 380 pi t plus b cos 420 pi t. Then unmodulated carrier power is 100 watts and the transmission efficiency of the AM signal is 40%. Find A and B. Okay. So here comparing this x of t with the standard equation, that is s of t is equal to AC cos 2 pi fct plus mu AC by 2 cos 2 pi fc plus fmt plus mu AC by 2 cos 2 pi fc minus fm into t. Okay. So this is the standard equation. We are going to compare this x of t with the standard equation. Okay. So here the given unmodulated carrier power is 100 watts and transmission efficiency is 40%. Okay. So carrier power PC is equal to AC square by 2. So AC square. So AC square is equal to 200. Why? Here PC is given as 100 watts. So 100 into 2, 200. So AC is equal to square root of 200. So you got 14.14. So this is the carrier amplitude. AC is 14.14 carrier amplitude. Another is eta. So efficiency eta is equal to mu square by 2 plus mu square. So the given eta is 40%. So eta is given as 40%. Transmission efficiency is 40%. So 40 by 100 is 0.4. So 0.4 is equal to mu square divided by 2 plus mu square. So after solving all this, what you got? Mu value as 1.92. This is my mu value, modulation index. From this, the sideband power you can take it as B mu AC by 2. Already find the AC value. You know the mu value. So substituting this value is 8.16. We come back to the this one. We go to find the A and B. Okay. B value is this one. A value is 14.4. 14.14. 14.14 is the A value and B value is 8.16. Okay. Yeah. Coming to the last problem. Calculate the total power in case of SSB technique. Here I am taking the SSB technique. A 500 watt carrier is amplitude modulated to a depth of 75% modulation. So 75%. How much power is achieved for SSB compared to AM and DSB SSC? Why? Because here AM is the basic one. The drawbacks of AM is reduced in DSB SC. What are the drawback? Already we discussed it. Power and bandwidth. Okay. So another name of AM is double sideband with full carrier. So that's why the drawbacks is coming. Here I am going to suppress the carrier, then it can be called as DSB-SC. But here the carrier is suppressed, but two sidebands are same. Again the same problem. So bandwidth and power is more. So again Another modification is SSB, single sideband. Here it going to cut one single band. So I am sending only one sideband, that is single sideband. Okay. So total power in AM is PT is equal to PC into 1 plus M square by 2. So this is the formula. Already we know that from the starting problem, first problem onwards. Same formula is using. PT is equal to PC into 1 plus M square by 2. So here you go to substitute the PC. So what is PC? 500 watts. So 500 into 1 plus M square. What is M? Modulation depth. A depth of modulation or modulation index, what it may be. So my M is equal to 75%. This is equal to 75 by 100. So it is equal to 0.75. So here you go to substitute these two values. What are the two values? One is a PC. PC is 500 watts and M value is 0.75. So substituting these two values in the given formula. So the total power is equal to 640.6 watts. Okay. So after finding this, what they ask, how much power is achieved for SSB compared to the AM. AM is the standard modulation. Okay. And DSB SC, double sideband suppressor carrier. Okay. So for that, here power saving in SSB with respect to AM. Okay. Is equal to PT minus PSB, sideband power divided by total power. So what is the formula for PSB? PC into M square by 4. So already given PC. You find M value. Okay. So my sideband power is 70.3. My sideband power is 70.3 watts. So power is in watts. So now we are going to find the how much power is saving. So PT minus PC divided by PT minus PSB divided by PT. So total power minus sideband power divided by total power is given how much power saving. So that is 89% is power is saving when compared with the AM and compared to the DSBSC. So what is DSBSB? So double sideband suppressor carrier is equal to 2 into PSB. So 140.6 watts. The sideband power of DSB is 140.6 watts. So power compared SSB with the DSB is 50%. Same formula going to substitute PT minus PSB by PT. Then you got. Why? Because here single sideband. So 50% is saved. Okay. So the references Simon Hacking and Sanjay Sharma, Jas Chitori, or books are used for developing this content. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.